Thank you very much. Okay, so lunar gravitational wave antenna. The first question might be, after the 4, soon 5 terrestrial detectors that we have, asking money for yet another 2 in the future, and these are being approved, if we need yet another gravitational wave detector. And good question. So the scenario is quite similar to what we know from the EM world. Over the next decade, 2 decades, we will have a wide band of observation frequencies, from the very low frequencies observed with the B-mode polarizations up to a few kilohertz with the terrestrial detectors. And now, of course, we are not continuously covering that band. There are some gaps, but one of these gaps is scientifically quite important as far as we know, and that's the decihertz band between LISA and the terrestrial detectors. And that situation is called the missing link. We have no very great idea so far what detector we could build to observe gravitational waves in the decihertz band. And that's where the moon plays a role. So what we propose is essentially the following. Well, that didn't work. I will try this again. I think that's not going to work. No, I have to somehow skip that slide. Okay. Anyway, that slide was supposed to show to you. Well, I'm not sure what's happening. Okay. Let me then try to skip it. So I skipped that slide. Explain to you. So the moon essentially acts as a receiver for space-time fluctuations. That means gravitational waves passing the moon induce quadrupolar vibrations of the moon, and the response of the moon is actually quite complex. So here are resonance frequencies of many quadrupolar modes of the moon, and we can simulate this in so-called null-mode simulations. Now these are quite reliable, at millihertz and a few tenths of millihertz, but in the very important decihertz band, they are not reliable. For example, the features that we currently see in these null-mode simulations, they do not reproduce at all the observations that we have from Apollo of meteoroid impacts, for example, which showed that the ground has very high Q values actually, and have very long observation times for individual events. So that tells us that the actual response at the decihertz band is much larger than what we currently see in these normal mode simulations. So we need finite element simulations that take topography and geology into account as much as we can and know, and then rerun these analyses. Now, what we propose is the deployment of 4 seismic stations on the moon in a of order kilometer diameter array. Now we need the array because we want to be able to distinguish in a better way between the seismic background that comes from moonquakes and meteoroid impacts and gravitational wave signals. And you can also see here indicated that we want to be in a permanently shadowed region. Now that is for us absolutely crucial because we need the best temperature stability that we can possibly get on the moon. And if it's cold, even better. But the temperature stability is really the key point here. And you find, of course, these regions at the lunar poles, and these are ideal. The moon is the key enabling factor, however, of the moon is that it is seismically extremely quiet, orders of magnitude quieter, several, I would say almost many orders of magnitude quieter than Earth. We have so far only upper limits set by the Apollo missions, but we have models as well, and they tell us that the moon is quieter by 6 to 7 orders of magnitude compared to Earth. And that is really the important feature of the moon, why it might work. Now, the payload is under development, of course, at the level of terrestrial prototypes, putting the sensor unit mostly together. Now, what we propose is that this is going to be a mechanical seismometer, essentially, with laser interferomagnetic readout. There are other options, but we are pursuing that street at the moment. And we have this cooled down to 4 Kelvin to be able to profit from superconductors or superconducting technology with niobium material. There might also be other options for that, but this is anyway the main, the baseline design that we are currently following. And that gives us something like, in the end, femtometer per square root of hertz sensitivity at 1 Hertz and sub-picometer at 0.1 Hertz. And that's what you need if you want to detect gravitational waves. Now, together with LGWA, we now proposed last year Soundcheck mission, which is essentially a geophysical explorer and technology demonstration for LGWA. So that is a single seismic station to be deployed in a permanently shadowed region. And here we target sub-picometer per square root of hertz throughout the decihertz band. Of course, this is really meant, in addition to being a technology demonstration, we have to understand much better the geophysical environment in a permanently shadowed region to have a better, to have more information about the seismic background events and so on and so forth. So, and this mission was now selected into ESA's reserve pool of science activities for the moon. Okay, we also have funded a lunar emulator. That's very tricky to achieve on Earth. So we are going to build a seismically isolated platform underground, more than 1 kilometer underground in the LNGS underground laboratories. These are famous really for dark matter searches and neutrino physics, but we are also having a spot there for this in-vacuum facility. So the goal here is to create the quietest possible platform vibration in terms of vibrations, and then to put the cryogenic sensors on that platform, and then to essentially assess their performance, well, mostly in terms of their vibration sensitivity. And so on these platforms, we will be able to demonstrate these picometer to femtometer sensitivities that we need for the moon. The sensitivity targets are these. Now, just to point out, I mean, maybe you're not familiar with these plots, but in any case, so with that type of sensitivity in that band, you will be able to see a wide range of masses, compact binaries. That means massive black hole binaries, intermediate mass black hole binaries, solar mass black hole binaries, noon star binaries, white dwarf binaries, any mix of them, intermediate mass ratio in spirals. Many of these sources connected to electromagnetic counterparts. And so that is an enormous science case. And of course, that has been known before. That's the reason why very ambitious missions like the SciGo and Big Bang Observer were proposed in the past to observe in that band. The range of observation that we can achieve, especially with the intermediate mass black hole binaries, would be a few tenths in redshift. And that is, of course, making this also a cosmological, not only an astrophysical mission. And that's where we stand at the moment. So we are having already a collaboration of close to 200 members now, working on the payload, working on the science case. And that is, of course, a lot of lunar science as well, not only gravitational wave science. And yeah, that's where I want to stop. Thanks.